Good morning. We are in topic 11 of Unit 7 on equilibrium. We are going to be exploring the solubility equilibria. So we're going to be introducing KSP is what we're talking about today. So first we're going to talk about solubility, or what's also called molar solubility. So it is defined as the amount of solute that will dissolve to form a saturated solution at a particular pressure and temperature. Okay, so we're dissolving some sort of solute, typically a solid, and we're forming a saturated solution with that. So when we're going to talk about what a saturated versus unsaturated and all that, those terms are in just a little bit. But we're going to talk first about how we write an equation for this and how we write our KSP expressions. So first, let's talk about the expression. So if we had chemicals like calcium hydroxide or iron hydroxide, and we wanted to show how they broke down, how they dissolved in water or to make a solution, we start off with the solid form, and we do not include water in the equation, okay? We're just showing how this chemical breaks down into its aqueous ions. So we'd have calcium ion and then 2 hydroxide ions, aqueous. So all the time this year that we spent practicing how to break down ions or ionic compounds, this is where it comes into play even more. Again, this would be a solid. We'd break it down into iron, and it would also have to be a 2+ because we have 2 hydroxides in this one as well. So very similar formulas for both, very similar equations for both. Now, the KSP expression, so let's talk about what that means. K is still our equilibrium constant, hasn't changed. We're just labeling it a little bit differently. SP means solubility product. Okay, so why is it called that? Well, KSP, if we look at it, we do products over reactants, concentration of calcium ion. Remember to use your brackets. Some of us are forgetting that. And we've got 2 OHs, so we're going to square that. Now, the reactant is a solid. We do not include solids in our expression. So that's why it's called solubility product, because it's only the products of that reaction or that equation that are included. So our KSP expression for the other one would be iron 2+. And again, hydroxide squared because of the coefficient. So those are expressions. We're not going to have denominators on these ones. So one of our questions here, why does solubility equilibrium expressions not have denominators? Because the reactant is a solid. All right. So it's always about dissolving that solid. So we're going to be excluding that from our expression. So let's look at a couple of statements here. So when a solution is in equilibrium, the concentration of the dissolved solution remains constant. Once we reach equilibrium, that concentration is going to remain constant. That's going to be true. Okay. Now, when a solution is in equilibrium, the solid salt is always completely dissolved. That is the part we're going to discuss further, which is false. Okay, we don't have to have everything dissolved to be at equilibrium. Okay, we can have some solid down at the bottom forming into ions and dissolving, and some ions forming solids. So we can get that equilibrium forming between those. So let's talk about this next part. So which salt is more soluble? All right, so we're going to be filling out some blanks in this table. So we've got our KSP expressions up here, but we're going to go ahead and also write their values. I'm going to give those to you. So calcium hydroxide has a value for KSP of 5.5 times 10 to the negative 6th, and iron is 8.0 times 10 to the negative 18. So we have a big difference between those. Remember that if it's to the negative 6th, that means we're moving the decimal 6 times to the left. To the negative 18th, we move it 18 times to the left. So this is a much smaller value for iron than it is for calcium. So what does that mean? First, which salt is more soluble? Calcium hydroxide is more soluble because its KSP value is larger, okay, KSP is larger, which means there's more product or ions in solution, so it must be more soluble. Okay, so when this value is larger, it means we're shifting a little bit more towards the products, not quite so heavy on the reactant side. So it's going to be more soluble. Okay, the bigger the value, the more product we're going to be forming, the more it's going to dissolve. Okay, so let's just make a note. Larger value. Sorry, I made that got a little weird. Larger value for KSP equals more soluble. Okay. So then, which salt most likely has stronger intermolecular forces with the solvent? So who's more attracted to the solvent? And we're going to explain how we know. So in this case, again, calcium hydroxide has stronger IMFs, or interactions, with the solvent. Remember, so that would be our like calcium ion, Ca2+, sorry, that's a Ca2+, interacting with our little water molecules, right, our Mickey Mouse water. So that attraction between those would be stronger than iron's attraction to water. Okay, so we know this because more of the salt is being dissolved into solution. So if more of it is dissolving, that means there's more ions, there's a stronger attraction to the water for calcium and hydroxide than there is for the iron hydroxide. So the water is able to break it up and form those ions. So let's take a look at this scenario. You have two flasks at equilibrium, one of aqueous calcium hydroxide and one of aqueous iron 2 hydroxide. Which flask has higher concentration of ions? Explain how you know. Again, if we want more ions, we would need a greater KSP value. So the flask with calcium hydroxide has a higher concentration of ions because it's more soluble, so more will be dissolved. All right, so this is just lots of explanation, thinking through what's going to happen with these, how do we compare KSP values. Let's take a look at the last one. So you allow the solvent to evaporate from your two flasks. Okay, so now the water's leaving, increasing the concentration of ions in each. Which salt would precipitate first? How do you know? So if it's going to precipitate, that means it's going to be forming the solid. All right, we're going to be going towards the solid side. So we want to know which one's going to shift first. Well, iron hydroxide will precipitate or form solid first because it has a lower KSP value, meaning it's less soluble, fewer ions can be held in solution. So it's like the water can only hold so much of each chemical, and it's not an equal amount of each chemical. It depends on the chemical and the attraction of the water to that chemical. So the more attracted it is, the more ions it can hold, and the more soluble it will be. The less attraction there is between our ions and our water, the less soluble it will be, and the less those water molecules can attract. And the reason why we have a difference here, our hydroxides are not necessarily the issue, it's our positive ion. Our iron is going to be a larger ion in terms of radius, and so that's going to decrease that attraction to it. Okay, so let's keep going. Now that we've looked at what these values mean, let's look a little bit more at their solutions. Okay, so let's talk about what's actually in the beaker. So when something dissolves to create a saturated solution, there are 3 points we can look at. So if we are below saturation, okay, we haven't saturated it yet. So saturation means it's like, imagine a paper towel soaking up water, right? That's saturating it. We're filling it up with that substance. So below our saturation, we can have more chemical to dissolve. So we've added some solid, and the solid, you can see the arrows here. So here's our little solid particles moving out, but there's more arrows going out. Sorry, I'm covering it up. There's more arrows going out in terms of, so if they're going out, that's dissolving. And if they're going in, that means it's precipitating or forming the solid. So there's more of it dissolving than there is precipitating. So that means that we're shifting it towards that dissolving side. We haven't saturated it yet. Okay, so our equilibrium hasn't been reached because we haven't filled up our solution with ions. Now, if we're right at saturation, no more can dissolve, but there's no precipitate. So all of our ions have dissolved, but we're not forming any more precipitate. So it's a clear solution. Clear as in there's no solid at the bottom. Okay, this would also be a clear solution with no solid. So it is a little hard to tell the difference between these. The only way to tell if we're at saturation is if we add a little bit more of our solid and it doesn't dissolve. That tells us we were at saturation. But it's kind of hard to tell with this one, the difference between them. Now, if we are above saturation, no more can dissolve, and there's excess is in your precipitate at the bottom. So it is got solid, there is solid, so solid present, and we've created so these are both at equilibrium for both of these two, okay? Because we've reached that point where no more can dissolve. We saturated it with however many ions we can fit there in both of these, but this one still has that precipitate, that solid at the bottom. Okay, so no more can dissolve. We've got that equilibrium between our ions dissolving and our ions undissolving. We're forming that precipitate. So this is where KSP comes into play, is with these two. So at saturation or above saturation, we can measure our KSP value, because that's the maximum amount of solute that will dissolve. Here we haven't reached our KSP yet because we can still dissolve some. Okay, so what does that mean for us in terms of calculations? How do we use this KSP value? Okay, so we're going to look at how to calculate first the solubility of a chemical. So for this, let's see if we can zoom just a tiny bit. Oops, sorry, actually, I'm a little bit further than I want to be. Don't think I can zoom that much. All right. So first for this one, we want to write the dissolution equation or dissociation equation for AgI. So basically, we've got a solid and we want to break it into its ions. Ag plus and I minus. And I know I is minus because it's in that 7th column, so that means silver has to be positive. Okay, so that's our equation. We've done that part. Check. You have a saturated solution of AgI solid in a 1 liter beaker. Calculate the concentration of I in the solution of, or if silver is 8.8 times 10 to the negative 7th molar. Okay, at this temperature, KSP is this. So we have a KSP, we have a concentration of one ion, we want the concentration of the other ion. Okay, so we can always write our KSP expression to help us. And then we can simply plug in the information we have. So we have 8.5 times 10 to the negative 17th equals, our silver is 8.8 times 10 to the negative 7th times our concentration of I minus. So if I want to dissolve for I, I'm going to divide by 8.8 times 10 to the negative 7th on both sides, and we're going to solve. So 8.5 times 10 to the negative 17th divided by 8.8 times 10 to the negative 7th, and we get we have two sig figs, so 9.7 times 10 to the negative 11th. So our concentration of I, 9.7 times 10 to the negative 11th. So that's how we can solve for our concentration. If we've got KSP, we've got a value for one chemical, we can solve for the other one. All right, now we're going to take a look at how to calculate the KSP value of a chemical. So like we've done before, if we want to find our equilibrium constant, then we need values for each of our ions or our chemicals at equilibrium. So again, we're going to write the equation for our dissolving of our solid, BaCl2 in this case. And when it breaks down, we get Ba2 plus, and we get 2Cl minus. So if the concentration of our saturated solution is 0.75 molar, determine the concentration of each ion in the saturated solution. Calculate KSP. So when our solution is saturated, the solution's molarity is 0.75. If we want to find the molarity of each of these, we need to do just a mole ratio. So from the, remember molarity is moles per liter. So if we're going from the whole chemical to just Ba, moles of BaCl2, to moles of Ba, 2 plus, when one of these breaks down, we get one of the Ba2 plus. So it's going to be equal molar, 0.75 moles per liter, or you can just write your capital M and then your Ba2 plus. Now if we did the same thing for our other chemical, our chlorine, moles of Cl minus, we can see that when one of these breaks down, we are going to make two of the chlorines. It's a 1:2 ratio. So we're going to end up with 1.50 molar chlorine ion. Okay, now I did this the long way and showed the whole mole ratio. That is not something you will have to do every time, but if you're more comfortable doing your mole ratio that way, you're more than welcome to. Another way is to say, okay, if BaCl2 breaks into Ba2 plus and 2Cl minus, and I know this is 0.75, it's a 1:1 ratio, so this is 0.75 molar, and this is a 1:2 ratio, so this is 1.50 molar. And you can just think through it that way and just process your information. Just as long as we're able to realize that we're producing 2 chlorines for every 1 barium, so it should have twice as many ions. So it should have twice the concentration. Now, if we want to find our KSP, we're going to plug this into our expression. I'm going to write my expression first to make sure I've got that. I'm going to square my chlorine, and then I'm going to plug in my values. So 0.75 times 1.50 squared, and I'm going to calculate that. So 0.75 times 1.5 squared, going to be 1.6875. So we've only got 2 sig figs here, so 1.7 in this case would be our KSP value. And again, no units because it's a equilibrium constant. Right? So that is above 1. That's telling us this is reasonably soluble. We're going to favor products in this. We're going to have a decent amount of ions being produced there. Okay. So that's another type of calculation we might be able to do with this. All of our same equilibrium stuff still applies. We can still use Rice tables, all of that. So let's take a look at the last ones here. So calculate the molar solubility of MgF2 when we're given KSP. So how do we do that? Well, molar solubility is basically what is the molarity of that solution when it dissolves. So what we want to do is find the concentration of our ions at equilibrium, and then determine what the concentration of the whole solution would be using a mole ratio. So we're kind of working backwards, using our KSP to find the concentration of our ions, using that to find the concentration or molarity of our original solution. So it's like the previous one, but backwards. Now, we can still start with our KSP expression. So I'm going to do that over here. Or actually, I would start with my reaction so I know how this is breaking down. It starts to become pretty obvious as we do these. Mg2 plus aqueous plus 2 fluorine aqueous. So our KSP is going to be magnesium 2 plus and fluorine minus squared. Now, we need to know how this would break down at equilibrium. Well, I don't know yet, but I can use a rice table. I'm just going to set one up right here with my reaction and think through this. So I've got a solid here. That part's not going to matter. We start out with none of our product. We're going to add some amount, x and 2x. So that's what we're going to end up with. So we can use that and plug into our KSP expression. We have our KSP value, 5.16 times 10 to the negative 11th, and figure out what these x values are going to be. So we're going to have x times 2x squared. This is where I often see issues, is students forget to actually square the 2 in the 2x. So if we were to simplify this, we'd get x times 4x squared. So that means we would have 5.16 times 10 to the negative 11th equals 4x cubed. All right. Next, to solve for x, I would divide by 4. So my x cubed is going to equal, so 5.16 times 10 to the negative 11th divided by 4. 1.29 times 10 to the negative 11th. And that equals my x cubed. So now I need to do the cube root of that. Now that's kind of annoying to do, honestly. So here's what I do. I've got my number. A cube root is basically raising it to the 1/3 power. So I'm going to do my caret key to raise it to the power, and I'm just going to put in 1/3 in parentheses. That's an easy way to do a cube root without having to use extra cube root buttons. So that's my answer. I'm going to put it in scientific notation because I got a lot of zeros there. So 2.3, we got 3 sig figs, so 2.35 times 10 to the negative 4. Okay, so that's my x value. That's my concentration of magnesium. 2 times that value would be my concentration of fluorine. But what I want is the molar solubility of the whole thing, the concentration of the solution. Well, we can see that this is a 1-to-1 ratio, magnesium to magnesium fluoride. So if magnesium's concentration is 2.35 times 10 to the negative 4th, molar is my concentration of magnesium ion, that is also equal to my concentration of magnesium fluoride. Because when I dissolve one of these, I get one of those. All right? So we could also multiply that by 2. And that would be my concentration. So 4.70 times 10 to the negative 4 molar would be my concentration of fluorine, if we needed that. Okay? So kind of using the idea of a rice table to help us figure out what would those be at equilibrium. They're going to start at 0 before they dissolve. And we're just adding the x values, matching the coefficients, and then plugging that into our KSP expression. Finding x. X gives us the concentration of each ion, as we can see here. That also helps us find the concentration of the whole solution, right? That 1-to-1 ratio. Okay. And then this part, we've actually already calculated the concentrations of our 2 ions in solution. So it kind of comes naturally with doing this, finding those concentrations. So we can do a lot of the same things, but with this that we can do with our equilibrium expressions. What's nice about this is we have a reliable mole ratio that these things are breaking into. So if I'm producing a certain amount of one ion, I'm going to have use that mole ratio to find the other ion, and it's going to be occurring that way each time. So that helps us in our calculations. All right, that's our last example for this. Work through your practice problems. Let me know what questions we have. Again, if it asks for molar solubility, that's just the concentration of your solution, your full chemical. All right. Have a great day, guys.